Sawyer-Roy, who's here. Okay, error-correcting codes are studying kind of the problem of trying to communicate over a noisy channel. This is a channel which will adversarially flip some of the bits of the transmission, and the sender wants to encode his message to kind of blow it up to be a longer string so that when it's transmitted, even if some of the bits get flipped or lost, the receiver will still be able to decode. In particular, they need two algorithms, an encoding algorithm and a decoding algorithm, so that this can work. And a natural question is kind of how much noise is it possible for the channel to have and still communicate successfully over it? And you can think for a minute, and it's not too hard. Communication is impossible when the noise rate is 1/2, because then the channel is just outputting a random string. But what about when the noise rate is slightly less than 1/2? Let's say 1 minus delta for some positive delta over 2. So in this case, it is possible. There's the Hadamard code, which has distance 1/2. And so you could use this to encode your message and then to decode, and then you could communicate this way. The Hadamard code isn't so great because it has exponentially small rate. And there's, so basically if you go back to this picture, what that means is that the encoder is going to have to blow up his message by an exponential factor in order to transmit it. And that's not ideal. And the Plotkin bound said this is essentially inherent. Any code that has distance 1/2 is automatically going to have exponential rate. And so sort of back to this question, what about efficient communication? Is it possible to use a noisy channel with noise rate 1 minus delta over 2 to communicate efficiently, i.e. without using the Hadamard code? And okay, you're basically here asking, do there exist codes that have distance 1 minus epsilon over 2, where epsilon is sort of chosen by you after you know the channel? All right, and so if you can choose such a code that has epsilon smaller than delta, then your channel will be able to support communication. And there's a sort of old probabilistic result that says a random code of rate epsilon squared is going to have distance 1 minus epsilon over 2 with high probability. This is the Gilbert-Varshamov bound. It's non-constructive. And then a few years ago, Ta-Shma, in a breakthrough work, showed that there's an explicit construction of such a code. It does slightly worse. Its rate is epsilon to the 2 plus little o of 1. And he gave an explicit construction. So this was fantastic. And so back to this picture, if the sender and receiver want to communicate using Ta-Shma's code, the encoder will sort of encode his message. He'll take, take the hit of an epsilon to the 2 plus little o of 1 factor, making it bigger. And then once the code word is transmitted over the channel, some of the bits are going to get destroyed. But because epsilon is chosen small in delta, there will still be information for the receiver to recover. And then the question is like decoding. Is it possible to decode this thing? And in particular, for what values of delta and epsilon is decoding possible? And Ta-Shma's work gave no decoding algorithm. It sort of left it open. And prior work of Geronimo et al. Shows how to decode for, basically when delta is bigger than we would like, basically. The requirement is that delta has to be bigger than this funny factor of epsilon, and it's not the parameter that we would like. So if you plot this on sort of a line where this is delta and the noise is increasing, like delta equals 1 is no noise. It's 1 minus delta is 0, so it's no noise. And then as delta gets closer to closer to 0, the noise rate gets closer to 1/2. And the prior work says that basically you can decode in this region sort of as long as you're above that point. So delta is larger than this value. It's clear that delta or decoding is impossible when delta equals epsilon. Sorry, that's supposed to be whatever. Basically because then the noise rate can kind of override the distance that you have. And there was a big gap here. And in particular, there's this thing called the Johnson bound, which is this kind of natural point. The Johnson bound is kind of the last place where you can generically decode, kind of no matter what code you have. In particular, like no matter what code you have, you'll be able to, information theoretically, recover, do some decoding as long as delta is larger than this Johnson bound. And there are some codes for which you can decode in this region, and there are some codes that you cannot. And in this work, we're going to show kind of how to decode all the way to the Johnson bound. So you kind of fill in this, and the picture looks like this. It's not clear. We definitely, our decoding algorithm fails, but it's not clear that it's impossible to decode this code in sort of this, and that's a great open question, is kind of what goes on in there. And I think that's all I wanted to say on the slide. Any questions? Make sense?
the left on if you go to the previous slide, in there is the unique decoding regime.
No, sorry, we're just kind of generically talking about list decoding. Unique decoding is possible whenever you're like above a quarter, basically, and then we're talking about the list decoding regime. Yeah. Yeah.
You said above the Johnson bound. Is there any combinatorial there?
It's a good question. So no, we don't have a combinatorial. Like the first thing you'd want to do is to kind of prove a combinatorial bound on the list size in this region. Above the Johnson, sorry, I don't understand your question. Above the, however, this isn't a formal statement or anything, but these SDP decoding things are quite flexible. My feeling is that if you had a combinatorial proof that the list was small, you might be able to get it to convert it to an algorithm just by kind of doing the proof on kind of the output of these SDP decoders, if that makes sense. Any questions? All good? Okay. So yeah, our main result is kind of what I said before, list decoding Ta-Shma's code to the Johnson bound, and you can read it. It's a theorem. Very nice. A couple things I wanted to say. Efficient here is kind of debatable, I guess. So like the decoding runtime is polynomial in n, but it's exponential in 1 over epsilon, which is bad. Typically in coding theory, there's like a tendency to treat epsilon as constant, but here you kind of want epsilon to go to 0 because you want to get your distance to approach a half. So having exponential in 1 over epsilon is bad. That's not good. And so an open question is, can you do it in polynomial in 1 over epsilon? That's a great question. Okay. Okay, so if you go back to, yeah.
Oh, I guess never mind. I guess the answer is, well, let's say just comes from the combinatorial bound. So the list size is just whatever the Johnson bound tells you the list size should be.
Yeah, the list, exactly, yeah. Okay, so if you go back to this picture again, okay, this is kind of to try to communicate over this channel with Ta-Shma's encoding and our decoding. So Ta-Shma's rate, so let's say you have the channel that has noise rate delta, 1 minus delta over 2. And okay, so you're going to use Ta-Shma's code with an epsilon that sort of has to be smaller than delta, which is going to require a rate of epsilon squared. However, because we only get to the Johnson bound and not to the full sort of capacity or whatever, we require epsilon to be less than delta squared. And so if you plug that in, the rate required to communicate over this channel is delta to the 4th. And actually, it's possible to do better. Like prior work already does better. These are kind of like concatenated codes coming from sort of larger alphabet Reed-Solomon type codes that have really good list size. And then you concatenate them with a binary code. And if you look at this picture, what's happening in these prior works is basically they're showing how to decode in this region for a code that has worse rate than Ta-Shma's. And so, you know, if like I guess, one really nice open question is trying to decode Ta-Shma's code here, which would allow you to beat this delta cubed, if that makes sense. Am I being clear? So we're not setting a world record because we're not getting all the way to the sort of capacity bound that we would hope. Okay. Questions? All right. So, sorry, was there a question?
Can you move back to the parameters?
Yeah. Sorry. Here?
Yeah.
Okay.
So I don't understand. Now you say you can decode up to delta to the 4, but before that you said you can decode up to epsilon square, or?
Yeah, so sorry, there are 2 parameters here. Delta is the rate of the noise rate of the channel, and epsilon is the like distance that you can protect against in your code. So yeah.
1 minus delta over 2.
Correct. 1 minus delta over. I keep saying delta and epsilon, but I mean 1 minus delta over 2 and 1 minus epsilon over 2. But basically, the noise rate of the channel is delta. That's the like 1 minus delta over 2 is the noise rate of the channel, and so what you would like to say is that you could choose any code that has distance that is bigger than the noise rate of the channel, which would mean epsilon is smaller than delta, in order to get a code that works. However, you can't do that in our code because, I mean, you can do that, but the decoding, you won't be able to decode is the point. You won't be able to decode unless you choose an epsilon that's like much smaller than delta, in particular smaller than delta squared.
So it's correct to say that the GR thing beats the Johnson bound?
Sorry.
GR beats the Johnson bound?
Yeah. GR gets all the way to more or less to here for a code that has worse rate. So basically, okay, I'm sorry. This is like not supposed to be confusing. It's my fault. What I'm trying to do is I'm trying to sort of connect the requirement for decoding, which is normally like in terms of the distance of the code, back to the kind of requirement of the channel noise. And when you do that, there's like a squared and then another squared. One of the squareds is from the GV bound. It's like epsilon squared is the rate. One of the squareds is from this Johnson bound. And so you put them together, you get like whatever the noise rate of the channel is, delta to the fourth is the size of the code words that you're going to have to use.
So can you decode up to the Johnson bound, or list decode?
Yes, we can list decode up to the Johnson bound, yes.
Okay.
So yes.
Now
Yeah.
I'm confused by the word channel. Is the noise random? Or?
No, we're doing adversarial noise here, yeah. Any other questions? Sorry about that. Bless you. Okay. Moving on to the rest of the talk, we're going to talk about how we decode. Now, there are a lot of pieces, and so we're going to focus on a few. In particular, this is an SDP decoding algorithm, and I wanted to make this talk accessible to people who weren't already experts on them. It will help if you're already an expert, then you'll be like, oh yeah, I know what he's doing. But even if you're not, hopefully we'll be able to like work through it together. So the key point, the thing I want to take away, or to me, this is the most important thing, is that when you set everything up right with this sort of SDP decoding algorithm and you sit down to analyze it, if you've done it properly, then the analysis of the decoding algorithm, it's the same as the analysis of the encoding algorithm. And basically what this means, if you know what this means, is that Ta-Shma's distance proof, it's like sum of squares friendly. It's a sum of squares proof. If you don't know what that means, it just means that SDP decoding kind of plays nice with the techniques you use to analyze these expander codes. Okay, and this has already been used like in other works. I think the work this morning, anyway, to Geronimo et al. There's a particular work of Geronimo et al. To kind of list decode other expander codes to the Johnson bound. And so using this kind of observation. So I want to start talking about like what are expander graphs, what are random walks on them, and in particular, I want to kind of set the notation we're going to use to analyze things further down the line. So expander graphs are like these kind of curious graphs that they're very sparse, but they're also very pseudo-random in kind of a technical sense that I'll explain. So notation-wise, G is going to be a graph. We're going to deal with functions, real functions defined on the graph. So these are like, it's equivalent to think of them as like real vectors where the dimension is the size of the graph, and that's kind of more normal, but we're not going to do that. We're going to deal with functions explicitly. And I'm going to sometimes write the functions as just like numbers on the vertices. And I want to establish these notations. These are kind of going to be with us for all of the technical stuff we do. And it's just mu and sigma, mean and standard deviation. So if I write mu or mu f for a function f, I mean the mean of f. It's just the expectation over the graph, over all the vertices of the value f of v. And sigma f is the standard deviation. It's going to satisfy sigma f squared plus mu of f squared is the like second moment of the function. Okay. And here's the definition of expander that we're going to use. We're going to say G is a lambda expander if for all functions f and g, you have this sort of concentration bound. What this says is that if you look at the product f of v times g of w over edges, vw, which are like correlated due to the graph sort of edge, the expectation of that quantity is very close to sort of the expectation that you'd expect if you just chose two random vertices. Okay, and the measure of closeness is going to be a function. It's lambda, which is like the parameter, and then the standard deviations of the functions. Okay, and this, oops. Sorry. So this is completely equivalent to just normal definition of like spectral expansion. It's going to be easier just because we're going to it's going to be fun kind of to work with these functions and play with their stats. And so we're going to see how it kind of plays out. We're going to use this. Okay, and when I say a random walk, I mean the process that chooses a random vertex and then sort of takes random steps. And this would be a random walk of of 6. So when I say random walk for this talk, I mean the number of vertices in the walk. Even though it's only 5 steps, I'm going to call this a walk of length 6. Okay, and the first thing I want to do, and this is really the only thing we're going to do that's like kind of got some technical gore behind it, is I want to prove a theorem on kind of the bias amplification of random walks on an expander. And this is kind of the engine that underlies a lot of the analysis of Ta-Shma's code and our decoding. And so everything gets more complicated because you're going to have to solve an STP and you get sort of different things. But the analysis that we're going to do here is really kind of the, I would say, the main sort of piece of techniques or whatever to take away from kind of this talk and this area, in my opinion. Okay, so if we have a graph and we have a function that's a pair, like a outputting plus or minus ones. I mean the bias is just the average of the function. So it's, if, yeah, this is the definition. By the bias of a function that's like parities, I just mean the expectation. And the question is kind of what's the bias of the random walk product function? So if you have some function that's defined on the vertices of the graph, and you consider the random walk version of the function, which is gonna, it's defined on a random walk of length t, and basically it's just gonna be the product of the base function on all the different vertices in your tuple. What's the bias of this? Okay, that's a question. And well, here's the claim. If G is a lambda expander, and the bias of f is, at most, you have some bound on the bias that's like related to lambda, then the bias of G is going to be this thing. Basically, it's going to decay exponentially with t. If you take t steps, then the bias is going to go from whatever it started with down to that thing to the t. Okay. And again, this is I'm going to prove this claim. But before I do, I want to bring it back to coding theory. And this is, again, it's the engine that underlies sort of all the Ta-Shma stuff, in my opinion. Other people might have different opinions, but this is my opinion. The use for codes is basically, what it's saying is that the random walk XOR code distance approaches 1/2 in kind of a technical, exponential sense. Sorry.
For Boolean or for any? Or
Boolean.
For real number?
These are Boolean codes, Boolean functions. Sorry, maybe I misunderstood your question?
So that's important for the page.
Yeah, to define the... Yeah, you can kind of generalize it, I think. There are different works that do it, but for this talk, I'm just talking about Boolean, yeah. Okay, so sort of before we... well, what do I mean when I say the sort of random walk XOR function? I mean, if you have, let's say this is like a random walk in your graph, and let's say you have some function which is defined on your whole graph, and this is what it says on these 7 vertices. Okay, the XOR, I just mean it's the XOR of all these things, which will be 0. Okay, so if the function evaluated at v1 is 0, the function evaluated at v2 is 1, et cetera, then the sort of the XOR function, which is evaluated at this whole tuple, is going to be the sum of all these, which is 0 in this case. Okay, and the use for codes is if you have a code, like a base code, which is defined, the coordinates are the vertices of the graph, you can build a new code. Oh, I'm sorry. Yeah, for any code, you can sort of define this plus minus 1 version of the code. And if you do that, then the Hamming distance of the code word, the Hamming weight of the code word, is related to the bias. It's basically 1 minus the bias over 2. And so you can do the same thing with the XOR code for this sort of XOR function G. And by the claim, what this is saying is that if you start with distance 1/2 minus 1 minus epsilon over 2, then the XOR code is going to have distance roughly 1 minus epsilon to the t over 2. Okay, so it has this sort of bias amplification, which converts it, when you go to the coding theory world, to essentially having the distance approach 1/2 in an exponential sense, if that makes sense. Any questions? Okay, so the proof is, here's how we're going to do it. We're going to start with k, sort of some parameter k. And for every parameter k1 to t, we're going to define functions fk, where the function fk, it takes in a vertex. And what it does is it sort of chooses a random walk of length k that starts at that vertex and then outputs the product function over that walk. Okay, and yeah, so that's what I'm saying. This expectation is over a random walk of length k that starts at v, in particular v1 equals v. All right, and what this means is that the function fk, as we've defined it, you can kind of factor it this way. It's going to be f of v, which is the starting point of all these walks, times the expectation over a neighbor of fk minus 1 of that neighbor. What I'm saying there is basically equivalent to taking a random walk starting at v is to take a random neighbor and then take a random walk of length k minus 1 starting at that neighbor. Okay, and then sort of the fun begins when you try to compute these statistics. Remember, mu is the sort of expectation of fk, and sigma squared is the variance. And if you break the function up according to this, you wind up with the expectation over an edge of f of v times fk minus 1 of w. And then use the expander mixing lemma. This is going to be sort of as though you sort of were taking 2 independent vertices here. Okay, so you're going to get sort of the mean of the function f, the mean of the function fk minus 1, and then you're going to have this error term, which is lambda plus the standard deviations. Okay, just expander mixing lemma. And okay, you start with the assumption that the bias that you started with is at most square root lambda. You sort of trivially bound sigma 1 by 1, and you get this, which is like the kind of stopping point of this first line. Okay, do the same thing now for the sigma term. So you're going to get sort of sigma squared, which is, at least the second moment of the function. And I'm doing the same thing, except now it's kind of, because the function's squared, you're taking 2 random walks out of V. You're starting at V and going k steps for one walk, and then starting at V and going k steps for the other walk. And if you look at the picture, you're kind of going to have this type of thing. And again, equivalent to doing that, to picking one V randomly and then taking k steps twice, is you can pick sort of like this structure, U, V, and W. And then you can take a k-1 walk out of U and a k-1 walk out of W. And that's all I'm saying here. And the nifty thing about sort of working with these parities is that the parity for V is counted twice, and it's going to cancel. So this sort of expectation, which has the f of V squared, that's just a 1. So it just goes away. And you wind up with this. And again, so basically V kind of factors out of this computation. You get left with like U and W. And U and W are random, pair of vertices that's 2 away. It's a random edge in G squared. And so you can use expander mixing lemma again, but now you're using lambda squared instead of lambda. And you get these 2 things. And this is kind of the stopping point. And all we're saying is you can upper bound the statistics, the kth level statistics, by k-1 level statistics, and then you use induction. And the claim just follows by induction. Super easy. And okay. So the random walk XOR code, let me have like a full slide on it. I mentioned it, but I'm going to say some stuff again. So the base code, you start with a base code, which is code that has some base distance 1 minus epsilon 0/2, some constant, but not optimal. You choose an expander graph after you start with the base code, where sort of the graph is going to have n vertices, and it's a lambda expander where you want lambda to, like root lambda equals epsilon 0, so that you can apply the thing, the bias amplification claim. And then the XOR code is this XOR thing that I had on the board before. It's like, for a code word in your base code, you're going to get a new code word, which is the XOR, the bit for the coordinate of the random walk of length t is the XOR of the base code word bits at those vertices. And the distance by the bias amplification claim is going to be 1 minus epsilon over 2, where epsilon is like, this term. It's lambda to the t over 2, basically. And the rate, if you do this out, it's going to be d to the minus t. Because you're blowing up, and you're converting sort of a code that has n coordinates, 1 for each vertex, to a code that has n times d to the t minus 1, d to the t. So kind of the rate blow up that you take when you do this is d to the t. And if you sort of, plug in an optimal like Ramanujan expander graph, you're going to get sort of whatever. And this is where you get sort of rate in terms of the distance, in terms of that epsilon parameter, is going to be epsilon to the 4th plus the low of 1. Okay. And this was kind of folklore, I think. It's sort of usually attributed to these like course notes by Bogdanov back in like the 2010s. Ta-Shma's idea is building on top of this, and he's using this kind of like S-wide replacement. It's essentially a de-randomization of this. He's not looking at all random walks. He's looking at only those which are these like S-wide replacement random walks, and sort of it's going to be essentially a pseudo-random subset of all the random walks, and he's analyzing that. But as far as like getting the techniques kind of into your head about how this works, we're going to just look at the vanilla, just this base XOR code. And everything's going to work kind of the same way. It's going to be kind of a matter of exporting the same ideas that Ta-Shma used to export these ideas up to his results to turn our decoding algorithm up to the full decoding algorithm, if that makes sense. Okay, so I'm going to just tell you now how to decode the random walk XOR code. Any questions so far? Okay, before I go, I want to mention that these techniques, essentially this like defining function game, and then you look at the stats of it, and then you like get this sort of bounding of the kth level statistics in terms of the k-1 level statistics and using induction. That's how all of the stuff, all of the claims that we're going to state are proved using kind of variants of that thing. And so I'm not going to really go super technical into exactly how the remaining proofs go, but it's basically that. It's basically that idea just kind of used in the analogous setting. Okay, so how do you decode the random walk XOR code? So this is going to be where the sort of SDP stuff comes in. So okay, again, you're given some corrupted code word, which we're going to think of as like y in this sort of plus minus 1. There's one parity for every random walk. And your goal is to recover some base code word, namely one parity for every vertex, which kind of is like, close to the corrupted code word. And I'm going to sort of represent closeness in this expectation kind of way. Okay, so the plan is step one is use the corrupted code word that's your input to set up some kind of like Lasser STP. If you don't know what that means, that's okay. The variables of your Lasser STP are going to be vectors. You have one vector for every subset of V of a certain size and every like proposed assignment to that subset. So yeah, you have basically a lot of variables. The number of variables is like n to the r, or to the, yeah, n to the r, where r is like the maximum size of the subset you're considering. And the intention of these variables, it's important to remember the intention. It's z of, like the variable for the subset and a is supposed to be 1 if a is the assignment that you're looking for. And it's 0 otherwise. Okay, and then there's going to be, like, it's an STP, so you're going to set up a bunch of like kind of semi-definite constraints. Most of them are Lasser constraints, which if you don't know what those are, it's okay. I'll kind of maybe mention a little bit about them in a minute. The only one that's kind of problem specific is this distance constraint, which says basically it's kind of requiring the solution for your STP to have kind of like to be close to your input, basically, and that's where kind of the problem comes in. The input to your problem comes in. Everything else is just completely normal Lasser STP.
Could we think of R as the length of the walk?
It has to be quite a bit more, but yeah, it's going to be related to that. It's at least that, and it's going to be higher. It would be great if the length of R could only be that, but because of kind of the ways that you analyze these like rounding and STP things in Lasser, it needs to be quite a bit higher. Yeah, again, it's poly n, but it's exponential in 1 over epsilon. It's going to be related to 1. Think of the R as like 1 over epsilon. It's the exponent. It's the exponent of n. Yeah, yeah. Yeah, correct. But you know, the log just goes. Yeah. Yeah. Okay. This is like an oversimplification, but here's what I wrote, and this is like more or less correct, at least. What I'm trying to do is I'm trying to say for every random walk v, I want to look at the assignments to the v that agree with the corrupted code word, and then I want to look at kind of the like norm of those vectors. I want to enforce that those vectors are larger than the other ones, if that makes sense.
So that's only for a small random walk. You already expect distance locally.
Yeah, and this is the expectation over all the random walks. So we want kind of on average the assignment that we're getting from the STP to kind of be close to the corrupted random walk corrupted assignment that we got to start with. So the outer sum is over all random walks. The inner sum is over the A's which agree with the corrupted code word that we got.
Okay, but the requirement is global because it's an expectation of all of them.
Correct. Okay. Okay, so if you don't know, well, I'll have a picture that kind of like doesn't really explain anything, but it's sort of an attempt to explain this. So if you don't know what this Lasser stuff is, that's okay. But here's what we're doing if you do know them. So if you basically, you use the Y to set up and solve some Lasser STP, and that's going to give you what's called a pseudo distribution on the set that we want. Then you're going to round the pseudo distribution using completely standard STP rounding stuff to get an actual distribution, and then you just output a sample from that actual distribution. Okay, if you don't know what this means, it's okay. Let me sort of have a picture or whatever. So essentially what a pseudo distribution is it's a family of little local distributions where each one is kind of defined on a small subset of the global thing that you want. So in this case, like the global, you want a global distribution on 0, 1 to the v. And what you have is like a bunch of little distributions which are defined on 0, 1 to little subsets of v, where the subsets are a fixed size r. And you could think of like obtaining such a family of like local distributions by taking a global distribution and looking at the like marginals. That would be one way to do it. If you did that, you would have some like consistency among the little like pseudo distributions. And the Lasser constraints are basically enforcing that you have similar type of consistency. But it's not true that every like Lasser pseudo distribution is going to kind of correspond to a real one. There are a lot of known examples, and like there's a lot of work kind of studying this. So basically, if you can see kind of the little, you know, I realize now this is like an eclipse themed picture. I didn't notice that until right now. But you have a lot of little local distributions which are sort of assigned locally everywhere, but it's not like you can sample. You can't just sample from each one independent. Like there's a lot of kind of correlation among them, basically. And what you're doing, the way that you kind of take that data and get an actual distribution, it's called rounding. But what you're doing is you're picking one at random, one local distribution. That's going to give you an assignment on the things in that set. And then what you're doing is saying, OK, for every other point, I'm going to choose a set that contains the set we picked and the point that we want. And I'm going to sample according to this sort of slightly larger distribution, conditioned on agreeing with like the sample that we already took from the smaller one, if that makes sense. Now you've kind of broken this sort of like local data that has lots of correlations into sort of, you're hoping that like all the correlations are kind of going to fit into the S that you chose randomly, and all the other stuff is going to be independent, and you're hoping that things will work out. That's called rounding. That's how you convert this like pseudo distribution into a real distribution. And the analysis, this is like the last slide. I put the sort of algorithm here. The overview of the analysis is basically two observations. The first is basically saying that the distribution that you obtain when you round, it's going to have this. It's going to basically be close to the base code word that you're looking for. So, so ZV1 is the bit that it's the bit that the distribution gives to V1. So basically, if you draw a sample from the distribution, the bit corresponding to V1, that's ZV1. Okay, and the way that you sort of can show that the distribution that you obtain in step 2 has this like being close to the code word you're looking for, I'm going to call it Lasserre gymnastics. Basically, it's very standard, and it's not anything new to our work at all. It was kind of already there in the other works. The new idea is kind of understanding, like you take this, and you kind of do the bias amplification thing to it. Like you build some functions, you look at their statistics, and then you get from this sort of claim that you have like agreement, epsilon agreement on a random walk, you get sort of back to having epsilon 0 agreement on a vertex. And it's the same kind of techniques as we saw for the bias amplification claim. Yeah, epsilon 0 is like the related to the distance of the base code. Epsilon is going to be epsilon 0 to the t/2 because we're doing the vanilla random walk. Correct. Yeah, exactly.
That follows just from knowing moments. You don't need to know more. You just need to know up to the kth moment, so that would follow.
Yeah.
The analysis.
Yeah, it's the same as the analysis. That's right. Sorry, did I answer your question?
Yeah.
That makes sense. Okay. And again, this is I said this, but you define functions, you analyze the statistics. You're going to use sort of these like bounds of the k statistics in terms of the k-1 to get all the way from the teeth level statistic, which is this, down to like saying that okay, the teeth level statistic is large, down to okay, the first level statistic is also large. And it's the same. And so that's it. So conclusion, to summarize, the distance analysis of Ta-Shma's original code gives the analysis of this Lasserre SDP decoding algorithm all the way to the Johnson bound. Open questions are, I mean, I'm just writing two. There are several, but improving the decoding runtime to get rid of the exponential dependence on 1/epsilon, that would be great. And improving the decoding radius to work, beyond the Johnson bound, obviously that would be great too. And that's it.
Question.
So for removing the dependence on epsilon, do you think there's a hope to stick to these SDP-based decoders and remove the dependence on epsilon?
Definitely, but I'm not sure about Lasserre. Like you probably have to move away from Lasserre because there are a lot of different like things you could try besides Lasserre. Lasserre gives you really kind of nice control. In particular, like the things you get out are these like probability distributions almost, and you can kind of work with them as if they are probability distributions. So it's really flexible, but it requires a lot of variables. So if you wanted to get rid of that exponential dependence on 1/epsilon, you'd I think have to move away from Lasserre. But that doesn't mean necessarily moving away from all SDPs. Like it might be possible to set up a different one and analyze it. Yeah.
Yeah, this is related. So this talk and the previous talk, a very similar format where the code is either a Tanner code or here you have these local paths. Then you define local distributions on them that are consistent, and then you use the SDP. And the question is, can you say something about like when do you expect this to work? And specifically, I think that maybe you can explain why you get this extra square. You needed your epsilon to be delta squared, if I remember correctly.
That's right. So, okay, that was two questions. The second one is it's those Lasserre gymnastics I said. There's like a Cauchy-Schwarz where you kind of square something and it just carries all the way through. Once you get to this claim, it's just like you've started with epsilon to the 1/2 and now you get to epsilon. So you've already kind of taken that squared hit and it's just in this very standard Lasserre gymnastics. Basically, it's because you're kind of proving the Johnson bound to some extent, which is just like doing a Cauchy-Schwarz or something. And if you wanted to sort of try to get beyond the Johnson bound, you'd have to do something more, you'd have to do something different. And in particular, I think it would be right to start with just trying to get a combinatorial list. Forget decoding, just combinatorial bound. And I'm sorry, you asked another question about the agreement, but I didn't quite understand. What were you trying to say?
I'm not sure I understand the question myself, but it's something like I want to understand when would this be expected to work? This kind of strategy where the first part is you define some kind of Lasserre where you have local distributions which agree, and then you have an algorithm that works.
Right. Yeah, it's a good question. I don't know myself. I'm not like the most experienced with this stuff. I did read a fair amount of like the works from like the 2010 area. And it seemed like the people who were kind of like figuring all this stuff out then, they had this idea that any technique that kind of, or I don't know, they had sort of like families of techniques that were SOS friendly and families of techniques that weren't. And as long as any technique you were using was kind of in the first category, it should work. And already people knew, like the Cauchy-Schwarz was an example. If your whole proof of distance just uses Cauchy-Schwarz, then it should be SOS friendly. It's not surprising in retrospect that like anything that's using the expanded mixing lemma, it's just some type of Cauchy-Schwarz. It's also going to be SOS friendly. So I'm not actually maybe an expert in like what you can use SOS stuff for and what you can't, which is maybe kind of what you're asking. But I think that those people probably wouldn't be surprised that the expanded mixing lemma is like you can use it. So, and like I said, there's all this other work that's more recent where people are using this to decode other expander codes to the Johnson bound, and it's kind of the same. Yeah. Yeah.
So is there hope for a combinatorial algorithm for such a thing? For example, even when the graph is complete.
So you're trying to remove the need for these like convex optimization and STP. It's a good question. So if you wanted to try to do something, the good place to start, because these are all extreme de-randomizations of just the complete graph. So start there, it might be easier. And even just don't do walks, just do 2, maybe.
Yeah.
And I'm not sure. It's something I've thought a little bit about. It doesn't seem super easy. I'm not positive, I guess. It shouldn't, there's no reason to me that it shouldn't be possible to do without STP. But I mean, aren't there all these works that are like trying to get around using STP to like max cut optimizations? Like, isn't that even in a simpler case where we don't know how to like do as well if we remove STP?
Like these regularity lemma approaches.
Yeah. So yeah, I think I'm not positive, but it doesn't seem like this would be too different from those anyway.
I think for the complete case, some sampling-based algorithms might work.
Other questions? We are at peak eclipse now, so we can go up.